Good afternoon, everyone. I will present the work entitled Some Strategies to Develop Promising Cathode and Anode Material for Rechargeable Magnesium Batteries. This work has been developed at the University of Córdoba in collaboration with the University of Xiamen, with the Professor Yang's group and Tirado groups. The outline of my talk includes the following points: a success story of lithium-ion batteries, search for efficient, safe, and alternative batteries, strategies to develop electrode materials for magnesium batteries. We'll see 3 different strategies, conclusion and perspective. Imagine a future where cars, bicycles, houses, boats, planes, factories are full of electrochemical storage systems for powering our tools' life. It could be the real scenario after a few years, as the development of a diversity of batteries will reach a diversity of uses. Lithium-ion batteries, a success story. The Nobel Prize in Chemistry was jointly awarded to Lubinov, Stanley Whittingham, and Akira Yoshino for the development of lithium-ion batteries. Many scientists over the world have been working on these 2 concepts, lithium metal and lithium ion, rocking chair, to finally develop the lithium technology that nowadays we know. These batteries are increasingly employed to electrify transportation and provide stationary energy storage for electrical grids. However, their development is still relatively limited, and their broader adoption will depend on their potential for cost reduction and performance improvements. The energy density and specific energy of this technology improved over the time. Here we have the range of 1990 till 2019. Over this period, the commercially available cells' maximum energy density increased over this time, including cylindrical, pouch cell, etc. Some projections intended to examine the differences in the underlying data suggest a nearly 20 years range for when prices might cross $75 per kilowatt hour threshold, and nearly 30 years range for reaching $20 per kilowatt hour. But this also causes concerns. The demand of critical minerals was presented in the COP26 Glasgow and dealt with a sustainable development scenario for battery storage and electric vehicles. It's foreseen an increased demand for the material presented in the table, such as lithium, graphite, manganese, nickel, vanadium. Thus, price fluctuation in this raw material can result in significant implications on the cell level cost of batteries per kilowatt hour. Since 2010, the price of lithium carbonate has increased 150%, while the price of sodium carbonate only increased around 17%. And their prices are listed on the figure. For example, nowadays, the cost of lithium carbonate is $13,000 and the sodium carbonate $150. It has been largely attributed to the limited geographical availabilities in lithium mining sources that drive up prices as demand batteries grow. By contrast, universal availability of sodium along with the mature soda ash mining industry keeps prices of sodium carbonate relatively stable. Also, increased safety is still required, since several problems found in electric devices, such as those from this picture, among the metal anodes, the high capacity, low reduction potential, and most importantly, dendrite-free deposition with 100% of Coulombic efficiency, some electrolytes make magnesium metal an ideal anode. The abundance in the earth crust and the price per metric ton make magnesium very attractive versus other divalent or trivalent metals such as zinc or aluminum. But the divalent nature of magnesium makes the diffusion of magnesium more sluggish than monovalent cations such as lithium. For this reason, there has been a growing interest in developing rechargeable magnesium batteries in the past decade, especially after 2013. The times cited and the publication over the time containing the magnesium battery concept is represented on the slide. And the most important research area are material science, multidisciplinary chemistry, physical, electrochemistry, etc. There are a large choices of composition from oxide, sulfide, phosphate, and also there are many mechanisms. You can see on the slide different mechanisms of reaction, intercalation, using 3D, 2D, 1D-dimensional materials, conversion reaction. Also, we can find some water co-intercalation reaction with vanadium, redox chemistry, and hybrid systems. As we can see, magnesium technology could be considered a rich system, but is still needed a mature technology. Let's see the first strategy we report here. It will focus on the activation of the vanadium 5, vanadium 4 redox couple in sodium vanadium phosphate compounds to increase the energy density. Previous literature reported the use of sodium vanadium phosphates, hereafter referred as MVP in sodium and hybrid systems. This compound has a rhombohedral Nacicon type structure with the space group R-3C, and it's a superionic conductor, with sodium located at 18E and 6B sites, with 8-4 coordination and 6-4 coordination respectively. Although this structure exhibits an open framework which allows rapid ion diffusion through the interstitial sites. However, for achieving a good electrochemical cycling, it's needed to enhance the electronic conductivity by the particles with carbon. The main building block involves two BO6 octahedra interlinked by 3 phosphates group lying along the Z-axis. As a result, the block aggregation, a three-dimensional framework with an overall composition of B2PO4 3 is organized. The redox property of this material allows to get around 60 mAh per gram per 1 electron. And the potential reaction at 3.6, 1.6, and 0.3 volts has been assigned to different redox couple when cycled in magnesium in sodium cells. In literature, it can be also found that zinc ions have been intercalated in the MVP structure, playing the vanadium 4 to vanadium 3 redox couple. But is it possible to activate the vanadium 5, vanadium 4 redox couple? Extensive investigations have been conducted involving the partial substitution of vanadium by other transition metal oxides such as chromium, conducting to the sodium 3, vanadium 1, chromium 1, PO4 3 geometry, in which the activation of the vanadium 5, vanadium 4 redox couple is possible. This material will be referred as MVCP. In the MVCP crystal structure, the octahedral BO6 interlinks via the corner with tetrahedral PO4 to form the three-dimensional B2 PO4 3 lantern units that are interconnected through PO4 with the neighboring units. 6 lantern units build up the primitive cell of MVCP, in which 2 different oxygen environment interstitial sites exist. Sodium 1 with 6-4 coordination and sodium 2 with 8-4 coordination, as we saw before. In sodium cells, MVCP exhibited a galvanostatic cure with a 2-step plateau at 3.4 and 4 volts with around 90 mAh per grams of capacity and exhibiting a 1.5 electron reaction due to the vanadium 5, 4, and 3 redox couple. Also, in previous study reported by Liu et al., it suppressed the irreversibility of metastable dissociative phases, highly dissociated phases. And this is possible to occur at -15 degrees. A preliminary study of this material in magnesium salt using activating carbon as anode and magnesium-based salt as electrolyte indicated a successful redox activity of vanadium 5, vanadium 4, vanadium 3 with the same capacity value as in the sodium cell. But the potential is lower. We have 3.5, 2, and 1.2 volts. The lower voltage recorded for this plateau correlated to the less negative redox potential of the magnesium to magnesium redox couple as compared with the sodium. Now, a deep analysis is performed in different magnesium cells configuration. On the left, we have one configuration. On the right part, we have another. On the left, metallic magnesium is used as a counter electrode and MgTFSI2 in DME as electrolyte. The galvanostatics and derivative curve shows the following characteristic. There are two plateaus at 1.7 and 2.3 due to vanadium 4, vanadium 3, vanadium 5, vanadium 4. Here at 25 degrees and at -15 degrees. Also, there are cathodic anodic feature at 2.3 and 1.2 volts. Also, there is a third plateau here at 1.2 volts that is due to the magnesium insertion. On the right, activated carbon is used as a counter electrode and MgTFSI2 in acetonitrile as electrolyte. The galvanostatic and derivative curve show that the capacity is around 80 or 85 milliampere-hour per grams. The different plateaus observed at 2.5, 3.5, 2 volts discharge, 1.2 discharge. At the efficiency is around 89%, the capacity is assigned to 1.5 electron, implying multi-electron reaction and the activation of vanadium 5, vanadium 4 redox couple. The low charge discharge hysteresis for a magnesium insertion is related to residual sodium reinsertion from the initial structure. In order to remove the contribution of mobile sodium in the initial structure, chemical dissociation of MbCp was tested according to the three reactions. For chemical dissociation, we use different oxidants, iodine, chlorine, and NO2-BF4. If we have a view to the example pattern, this sample shows a shift of the reflection to high angles, which is reflected by a decrease of the cell parameters. For the sample treated with iodine, the decrease of the cell volume to 1,361 cubic angstroms, involved a cell contraction of 4%. The stronger oxidants, chlorine and NO2-BF4, induced a cell contraction close to 7%, involving a more effective dissociation of the latter. ESPS spectra of the dissociated sample confirmed that chromium didn't show significant changes in the profile, implying that chromium remained inactive after the chemical oxidation. However, the vanadium spectra show the peaks became broadened and mostly asymmetric when treated with these chemical agents, indicating the appearance of new transition which would be ascribed to vanadium oxidation to the tetravalent state in blue here, and in pentavalent state in green. We observe pentavalent vanadium, especially with chlorine and NO2-BF4. In the standard 51 vanadium NMR method, signals of vanadium 3 plus and vanadium 4 plus are not active, while vanadium 5 plus compounds without localizing the electron could be observed. The MbCp material charge up to 90 and 81 mAh per grams exhibit clear signal at 824 and 944 ppm, with their corresponding spinning side bands, respectively. These signals are located in the region ascribable to the existence of vanadium 5 plus, which is temporarily assigned to sodium 1.47 vanadium chromium 1 PO4 3 and sodium 1.55 vanadium 1 chromium 1 PO4 3. Sodium and magnesium test cells are assembled with this de-Sovieti sample. The left part, the middle part. For iodine treated sample, the profile agrees with the expected insertion of sodium ions into chemically de-inserted sodium 2 sites and vanadium 4, vanadium 3 plus reduction at 3.4 volts. In the right part, a quasi-plateau at around 1.2, 1.3 volts on this chart is assigned to the insertion of 0.5 magnesium ions. On the following chart, we observe that the capacity increases till 92 mAh per grams, meaning that not only the 0.5 magnesium ions are extracted, but also sodium ions from sodium 2 sites. The poor electrochemical response in sodium and magnesium cells was confirmed when the sample were treated with chloride and NO2-BF4 treatment, which led previously to electrode deterioration due to this high oxidant power of these materials. The 23 sodium NMR spectra is shown here. The spectrum of the original MbCp sample exhibits two main resonance at -4.5 and 162 ppm. They can be assigned to the partially filled sodium 2 sites and the fully occupied sodium 1 site, respectively. The occupancy ratio is sodium 2 to sodium 1, 1 to 2 in the Nasicon structure. When removing 1.5 sodiums, the intensity of sodium 2 peaks decreases or even disappears. The sodium 1 peak broadens and shifts. Only small changes in sodium 1 peak intensity are observed, consistent with the relatively small lattice parameter changes seen in XRD. These results are reasonable because the sodium extraction is coincident with vanadium oxidation, which is expected to result in an overall shift of the 23 sodium resonance. Also, the small change in sodium 1 peak intensity is consistent with the relatively small lattice parameter change since XRD. The sodium 1.5 vanadium 1 chromium 1 PO43 sample was used for inserting magnesium at -15 degrees. The curve exhibits a fair discharge capacity reaching 90 mAh per grams. The composition after chemical treatment, after insertion of magnesium, were further checked by ICP analysis. So we can confirm the formation of sodium 1.5 and the insertion of 0.75 magnesium corresponding to this capacity. The strategy number 2 consists on the activation of the vanadium 5, vanadium 4 redox couple and use the inductive effect of fluorine, using different sodium to vanadium ratio in Nasicon type compounds, such as sodium 5, vanadium 1, PO4 2, the use of fluorine in sodium vanadium phosphate with different vanadium to sodium ratio is studied into the morph, this composition. Orthorhombic and trigonal MBPF with an Nasicon structure has been shown to exhibit excellent capacity retention over 1,000 cycles previously. Both the morph exhibits a larger structure. The BO4F2, BO4 infinite layer consists of corner sharing BO4F2 octahedra and BO4 tetrahedra, parallel to the 001 AB plane and stacked along Z-axis. Specifically, the layer contains two kinds of chains, chain A and chain B, which are alternative arranged and interconnected by corner sharing with the BO4 tetrahedron. The three-dimensional bond balance sum mapping suggested the diffusion pathway in orthorhombic MBPF, which is discontinuous along B axis. Therefore, the sodium ions are more likely to diffuse along the AC plane. However, for trigonal MBPF, the three-dimensional bond balance mapping shown that the sodium ions prefer to diffuse along Z-axis. Due to the differences on the staking of the AB chains, these orthorhombic and trigonal phases, the electrochemical property differs, being the trigonal MBPF the best choice due to the diffusion of ions along Z-axis. Taking the advantage of the reported results on sodium cells, as we saw before, we studied the adaptability of this material for magnesium cells. On the left is depicted the projection on the AB plane of the structure of trigonal MBPF. On the right, the three different tunnels in the structure running along the Z-axis, which are labeled T0, T1, and T2. The tunnels T0 and T1 are very similar, and they are formed by 3 BO4 and 3 BO6 units that share in corner. On the other hand, the tunnel T2 is formed by the apical corner of 6 BO4 units. There are 15 sodium atoms in the unit cell. 9 atoms are linking the slabs, thus participating in the framework. These atoms are not expected to be extracted. The other 6 sodium atoms are located in the tunnels, 2 sodium atoms per unit cell in each tunnel. A priori, these sodium atoms are expected to be inserted electrochemically. Then the tunnels are available to insert sodium ions as detailed results and discussion section next. The electrochemical performance of trigonal MBPF is tested in magnesium cell. For comparison, hybrid cell using sodium electrolyte and magnesium metal anode is displayed. All the cell has been cycled between 2.5 and 0.1 volts versus magnesium under the same condition. On the left, we observe two charge plateaux at 1.7 and 1.75 volts, giving rise a capacity of 68 milliampere hours per gram. This capacity matches well with the extraction of 1 sodium ion from the trigonal MBPF. The next discharge exhibits 2 voltage counterpart plateau as 1.6 and 1.5. The experimental voltage difference is 1.8 volt, which differs notably from the expected theoretical potential. In magnesium cell, 2 sodium ions are extracted after charging at 2.5 volts, delivering a total capacity of 136 milliampere hours per gram. On the end discharge, the capacity is recovered until 141. This capacity implies the insertion of 1 magnesium ion. As we can see, the charge also exhibits the same plateau as in the hybrid cell of magnesium extraction. A cyclic voltammetry curve further confirms the observed profile in the static profile. The capacity retention of this magnesium cell is around 44%, and 89% under 25 and 10 milliampere grams over 25 cycles, respectively. Table 1 contains the atomic position occupied by all sodium atoms in the trigonal P3 structure, as well as their location in their structure. Having a look to the tunnel, the sites sodium 9 in T1 and sodium 8 in T0 are very similar. In the same way, the sites sodium 4 in T0 and sodium 5 in T1 are also very similar. Finally, the two sites in T2, sodium 6 and sodium 6, are also in similar coordination. The sodium extraction in magnesium cells involve a decrease in unit cell. Experimentally, the sodium extraction, one sodium extraction from vanadium 5 P1 PO4 2 F2 sodium cell results in a volume reduction of 3%. This is theoretically. Ex situ XRD detected an anisotropic variation of the A and C parameter. Thus, an expansion of the cell in the direction of A is recorded, while the parameter C appears slightly contracted. After a full discharge, a direct proof of magnesium insertion is observed due to the notorious increase of the lattice parameter. Galvanostatic intermittent titration technique is applied to record one cycle at a quasi-equilibrium state. The calculation of diffusion coefficient could be expressed using this equation. The apparent diffusion coefficient during charge, which is sodium ion extraction magnesium cell, adopts a value around 3 times 10 to minus 9 to 2 times 10 to minus 11 square centimeter per second, which is the oxidation vanadium 3 to vanadium 4. And around 2.2 times 10 to minus 12 square centimeter per second after the oxidation up to vanadium 5. During the discharge, magnesium ions insertion in tunnel T2 adopts an average value of 2.2 times 10 to minus 13 square centimeter per second from 20 to 80% of the normalized capacity. But the diffusion coefficient at high potential is somehow higher. These results indicates that magnesium ion diffusivity is relatively high, whose values are comparable with other cathodes such as vanadium disulfide. On the right, it's shown the calculated voltage as a function of magnesium content in its composition, the trigonal MBPF. According to calculation, the most stable site for the initial magnesium insertion is the sodium 7 in tunnel T2 at 4 volts. After this first step, the calculated voltage for the insertion in tunnels T0 and T1 is very similar. The calculated volume variation during the insertion of one magnesium per fluoride unit to give this composition is less than 1%, making this material an interesting candidate for magnesium insertion. On the left, we represent the manganese 2p core levels. The original sample displays peaks typically of vanadium 3+. The charged electrode exhibit broadened peaks due to the observation of tetravalent vanadium. The extraction of a second electron involved a significant increase of the contribution of the pentavalent ions of vanadium, thus evidencing the electrochemical oxidation from sodium 5 to sodium 3. On discharge, the same pole recovered the trivalent oxidation state with some traces of tetravalent state. This result confirmed the reversibility of multi-electron reaction. Bottom right, here we have recorded the magnesium 2p, magnesium 2s, magnesium 1s core level. And they detected that after insertion, we observe an additional signal, which is in blue, due to the existence of magnesium ion with PO4, 3, and F fluorine surrounding atoms. More analysis by EPR and NMR are shown here. On the left, pristine sample present an asymmetric signal without any hyperfine structure. The G factor allows assigning the signal to vanadilyl ion. The stabilization of vanadilyl ions in trigonal MBPF as defects can be achieved through fluorine substitution with oxygen. The anionic substitution can take place easily due to the existence of BO4F2 BO4 infinite layer. On charge, the APR signal decreases smoothly, appearing diamagnetic vanadium 5. After charge and complete discharge, EPR signal is not recovered completely, which is related to the formation of sodium 3, magnesium, vanadium PO42F2, where magnesium ions prefer being coordinated with oxygen ions, affecting the stabilization of the vanadilyl ion. On the right part, we try to prove the redox property of vanadium 5, vanadium 4, vanadium 3 active center. After partial and total charge, the 51 vanadium spectra exhibit clear signal at minus 596 and minus 597 ppm with their corresponding spinning sideband, respectively. The signals are located in the region ascribable to vanadium 5+. Mention the composition in the upper part is worthy because this composition is after the electrochemical reaction. We confirm the oxidation state. The 31 phosphorus NMR spectra is also provided here. In the original sample, this spectra suggests that the observation of a dominant intense resonance signal 2065 ppm suggests the presence of a unique 31 phosphorus local environment. Based on the Rietveld refinement and the visualization of the structure, the P104, P204 tetrahedra lie in a symmetric environment in which each PO4 tetrahedron is connected with distorted BO4F2 tetrahedra. Each PO4 tetrahedron has in common the connection of, as we can see here, the connection of equatorial and axial BO4F2 distorted octahedra. After a total charge, the sodium extraction provokes the disappearance of the signal of 31 phosphor. Then, after a complete discharge, we observe that the signal is recovered. It seems that here, the oxidation of vanadium to vanadium 4, vanadium 5 creates a diminishing effect in the resonance signal of 31 phosphor. Finally, the third strategy is based on the use of carbon-coated or silicate, magnesium manganese silicate, and the use of hybrid concept using protons. The magnesium manganese silicate with olivine structure consists of a distorted hexagonal closed-packed framework of oxygen-building tetrahedral sites occupied by silicon and two octahedral sites. First, M1 occupied by magnesium and M2 occupied by manganese. This compound may reach a theoretical capacity of around 313 mAh per grams for one the inserted magnesium. The lowest barrier for magnesium diffusion was found in the C direction with 0.7 electron volt. In contrast, the diffusion in the A direction exhibited an extremely high energy barrier through passing the 3 electron volts. Many reports on this material are found by the Professor Wang's group, and the calculated voltage are still lower than the theoretical ones. Therefore, to get cathode material operating at high voltage and overcame the electrostatic problem of bivalent magnesium ion, novel scientific strategies should be taken as presented here. A carbon-coated magnesium manganese silicate has been successfully synthesized by a cell-sorted method. The crystallinity and phase structure is determined by X-ray diffraction. The Rietveld refinement confirmed the adequate indexation of the space group, P, B, and M, of the orthorhombic system. calculated parameters are also presented here. The sample is characterized by a crystalline, well-shaped nanoparticles around 90 nanometers with good uniformity. A close inspection by TEM reveals that carbon is uniformly coated on the particle surface. The small particle size is beneficial for ion diffusion, and an homogeneous carbon coating would facilitate the electron transportation. EDX maps reveals a uniform distribution of the constituting element on the particle surface. We adopt an alternative approach of engagging water traces in a conventional no-aqueous solution. After a charge activation cycle, more detail about it can be checked in reference, the electrochemical reaction of magnesium cells occurs between 2.8 and 0.5 volts versus magnesium, with 160, 150, 162 mAh per grams of reversible capacity, when water 0.4, water 0.8, and water 2.0 is used in the electrolyte composition. The reversible reaction is thermodynamically favorable in M1 sites, as we can deduce from the derivative curve, the inset of the galvanostatic curve. The capacity retention is better for the electrolyte-based cell using few water traces, as represented here. In the initial cycle, proton insertion would account for around 40–50% of the overall capacity. The occurrence of a hybrid magnesium proton electrolyte solution could provide superior mobility as compared to the sluggish magnesium ion. Indeed, other authors have proved already the magnesium ion migration energy barrier of B2O5 that can be decreased gradually with increasing the proton concentration. Symmetric magnesium electrolyte magnesium cells reveal that the electrolyte-electron interface resistance decrease in the presence of water traces. We can see here this no water. When we increase the amount of water, is decreasing the semicircle, enhancing the migration of magnesium through the magnesium oxide layer. The performance at different rates has been also obtained, and we can see the capacity fluctuated from 160 to 80 hours when we change the current rate density between 20 and 250 milliamperes per watt. 25 magnesium NMR detected an increase of isotropy around magnesium ions in the presence of water traces, black no water traces, in color different water. This fact can originate an increase of the electrolyte solvent mobility due to ion pair formation in the water-containing electrolyte. The result suggests an increase of symmetry close to exact coordination because of the solvated structure of magnesium with 6 water molecules appear at the chemical sieve of 0 ppm. Most probably, the water molecules displace the Me1s as a first shell coordinate. A satisfactory time-dependent stability of the electrolyte is found also when they have been kept under air atmosphere during 6 months. The line width was preserved, as we can see. However, the water-free electrolyte suffered an increase of the line width higher than 15 ppm, which correlates with the null electrochemical activity. ESPS assessed the manganese oxidation state at the manganese to core levels. Overall, magnesium extraction is evidenced by the expected higher binding energy shifting after charging and discharging. The significant contribution of trivalent and tetravalent state in the original sample must be ascribed to some unavoidable oxidation of the particle surface. On partial charge and eventually full charge, the relative contribution to manganese 3 and manganese 4 significantly increased, as we can see here, manganese 3 in blue, manganese 4 in green. After a complete cycle, the relative contribution manganese 2 reach the original value of the original sample. Thus, the reversibility of magnesium proton co-insertion into the carbon-coated magnesium manganese silicate sample can be directly inferred by the redox activity of manganese atoms. Also, by EPR, the spectrum of non-cycle electron material consists of a single Lorentzian line with G factor close to 1.9988 that is assigned to manganese 2 ions in the structure, close to the calculated G factor near to 2.0 for manganese 2 ions in a paramagnetic state. After partial and total charge, the EPR spectra is broader and features a higher G factor. Most probably, the manganese with an oxidation state, manganese 3, manganese 4, appears together with manganese 2 ions, contributing to the broadening of the signal. Although manganese 3 plus is a 3D4 electronic configuration, is not measured by EPR in the X-band region, manganese 3 plus coincides with manganese 4 plus at the end of the total charge, in agreement with ESPS results. Small differences in the intensity of SiO4 modes show that the orthosilicate framework was slightly modified after proton insertion, as we can see from the infrared measurement. The intensity broadening of the peak at 1,120 and 1,000 centimeter minus 1 is greatly influenced by protons and due to the silicon to oxygen to silicon asymmetric stretching. The intensity of silicon to oxygen stretching vibration peaks appearing between 1,550 also decreased. After one cycle, the suggested hydrogen 0.4 manganese, magnesium 0.8 manganese 1 SiO4 stoichiometry is deduced. By proton magnetic resonance, the occurrence of larger spinning side bands as a consequence of the proximity between the proton and paramagnetic 3 plus. As a conclusion, we can see that sodium vanadium phosphate with this Nasicon structure are considered promising material for developing magnesium battery for stationary application. The partial substitution of vanadium by chromium leads to increased energy density due to the vanadium 5, vanadium 4 redox couple. By selecting different sodium to vanadium ratio and fluorine ions, it's possible to get an inductive effect in the Nasicon structure for developing multi-electron reaction in magnesium cell. The electrolyte is considered as an electrochemically active partner, only a transmitter of magnesium ions, but also a source of protons. In fact, the electrolyte composition plays an important role. Full magnesium ion cell will be assembled in the near future, and the potential anode will be lithium titanate, carbon, or some silicate with partial extraction of magnesium is proposed. Finally, I would like to acknowledge you for your attention and also to some institutions who support this research. From Spain, from Gobierno de España, Ministry of Science, Education and Universities, through this project MAC 2017, also to the Ministry of Education and Professional Formation through this grant for doing research at Overseas Center, regional government Andalusia to the research group, federal funds here. Also, I have acknowledgement to the Xiamen University, to the group leader, Professor Yang, and his research group. Thank you for your attention. And if you have any question, don't hesitate to contact me to the emails I put at the beginning. Thank you.